Hello, everyone, and welcome to today's virtual Fireside Chat, Unisys machine learning story on neural network document search. So my name is Jade Denson, and I'm the Director of Member and Community Engagement with the Minnesota Technology Association. Really quickly, for those of you who have never engaged with us as a technology association, MnTech really prioritizes three things. First is driving policy and advocacy for our tech ecosystem. The second is partnering with companies and organizations to address some of the tech talent issues here in Minnesota. And the third is building community. So really bringing people together to connect, share best practices, learn, and have some fun, in all honesty. So today is really about that third pillar, which is bringing people together to sit by the fire and learn more about machine learning stories using Unisys as a case study. So I'm going to get out of the way so we can hear from Mark. We also have Kelsey on the line to answer questions and dive into some of the content as well, for them to introduce themselves and go into all things machine learning and how they've adapted that technology within Unisys. So let's get out of the way and let's kind of cozy up next to the fire and get going.
All
Mark,
right,
you can
thanks.
kind of take it away.
Yeah, thanks for the intro, Jade. So I'm Mark Rosno. I'm an engineer for Unisys. I work on a team that focuses on creating AI machine learning solutions for existing products within our wide suite of products within Unisys. So today we'll be talking about one proof of concept we did for our OS 2200 product, which is, for those of you who don't know, it's a enterprise mainframe system. And so there's a lot of proprietary code and proprietary languages that go along with that. So we'll be talking about what we did to implement and improve our documentation search.
And I'm Kelsey Brousseau, and I've had the opportunity to work with Mark on this great project and explore this wonderful new technology. Thanks for joining in today.
Thanks, Kelsey. So I want to start off today just to talk about a topic that all of us use on a day-to-day basis, which is search. Along with the internet, we've really come to expect that just about any piece of information that we want to access, we can find just by searching for it, whether it's with Google or other sorts of engines. So for example, what are the best local restaurants? When is the next season of my show coming out? Or in work life, how do I actually work with PowerPoint or other tools like that? What is syntax for common languages that I might work with? And especially as a developer, how do I solve this bug? Because I think a lot of our job today and a lot of the things we run into, really the ability to search for existing information, use existing solutions, and apply those to our problems within our companies is extremely important. And when we have commodity software, when we're using commodity languages like Python or the Microsoft suite, Google is a really good source for that. But when you're working in proprietary languages or proprietary systems where the information isn't actually in a public search engine, there's other issues that we need to encounter and other ways that we need to be able to access our search. So for Unisys, when we're looking at OS 2200, we have a wide variety of documentation and a huge amount of information that's accessible to both our engineers who develop the product and support the product and our clients who work with it. So these range from our programming languages that we work with, our proprietary concepts that are unique to some of our systems, and as well as administration and documentation like that. So our whole suite of documentation just for this one product is hundreds of documents, tens of thousands of pages that range from PDFs, Word, XML, and other formats. And in addition to that, we have a wide variety of informal materials, whether that's white papers that we've released, student guides from training our engineers, and just general reference materials. So in order to access this, our current existing system uses a traditional keyword-based search, and you're probably familiar with this type of approach, where the search takes the phrase you give it and looks for either exact phrase matching, partial phrase matching, or individual word matching, with the hope that the sections of the document that contain those keywords are what you're looking for. And when you know the exact keywords you're looking for and you know the exact document, this can work really well. So if you look, for example, on that bottom right-hand side, if I know exactly I want to look for the sec dollar user ID dollar call interface, I can easily find that. But if all I know is I want to access a security call interface to enter access user IDs, it's a lot harder to get to that information. And some of the issues and challenges we run into this are especially since we use natural language to search. The meaning that we're looking for and we're trying to find is actually encoded based on the context that we're in. And for us here, this is our OS 2200, but for another type of product or software, you have your own context where you have your own jargon, your own concepts that don't necessarily map to a normal English understanding. So for example, just in a general English sense, a word like ship could be, depending on the context, a noun, it could be a verb, it could be an acronym that's unique to your system. And you want your search system to really be able to distinguish between these possibilities based on the syntax that it finds. And especially one of the issues that we run into at Unisys with this search is, since our products have a long legacy, there's a lot of unique jargon and unique concepts that don't really map to a typical English understanding or even a typical software understanding when we're trying to have newer engineers come in and support the system or develop on these systems. One example of this, just in a more general software context, is if you work a lot with processes, multi-threading, it might be normal for you to make a search along the lines of, how do I kill a parent without killing a child? Which, if you work in that context, makes complete sense. But to a normal non-computer science user, you kind of look like a serial killer. And really, with our search, we need to be able to understand that we exist in a specific context and that our searches and our documentation also exist in that context. And so when we do the search, we want to be able to support that specific semantic meaning across our domain corpus. And to kind of dig into the potential searches that we might run into, if someone is running into an issue with the machine, maybe it stopped, there's some error message, you might have searches along the lines of, why did the machine stop? What is the root cause of the failure? And maybe the extrusion machinery trouble report. And within our document text, we have a sentence along the lines of, a failure in the extrusion system occurred due to X. And so if you look at just a keyword type search, if you don't know that the correct word is extrusion, or you don't use the word system, your keyword search isn't going to be able to find this document and this part of the document that contains what you're actually looking for. And so really the open question that we were trying to solve at the outset of this proof of concept was, how can we search our documentation while preserving our specific semantic meaning? And the answer that we ran across, and the solution that we'll be talking about today, is to use a sentence level semantic embedding with the state-of-the-art SBERT transformer models to be able to perform sentence comparison from the user's input query with the sentences in our documentation. And so if that doesn't quite make sense, we'll go through kind of a history or recent history of some of the developments in natural language processing which make this possible. So within the last 5-6 years or so, there's been a huge explosion of natural language processing. And really kind of the first big piece of that was in 2014, a project called GLOVE, which gave a word level embedding for vectors for English words. And so what it did is really do a linear regression style model based on the occurrences of words, which words occur near each other, and use that to map to a space like you can see on the right-hand side, where similar words like niece, aunt, sister are near each other. And also the relationships between similar words like brother and sister, aunt and uncle, have the same sort of idea in this space. And then with that idea in mind, we started looking at the encoder and decoder style of models in order to take an input sequence like man with high intelligence and map it to another sequence like a very smart man. And so in order to do this, you have two sides of the processing. There's an encoder side and a decoder side. And originally here it used an LSTM. And between the LSTMs, it passes information about which of the parts of the input were important to generate which of the parts of the output. And within a natural language context, we call that attention. And very quickly, people caught on to the idea that the attention mechanism there of saying that within a sentence, you know, word A is very important for understanding word D, that really caught on, and we actually removed the whole LSTM neural network part of it and focused on just the attention mechanism. So here you still have in 2017 the new transformer models that start to appear, where you still have the encoder, you still have the decoder on the other side, but instead of using a convolutional network, you just focus on the attention mechanism and use that to feed forward to both sides. And what this enabled in 2018 was a vast change in what was possible in state of the art for natural language processing, where you see the emergence of these projects like BERT and GPT-2 that took this transformer stack and said, we can split this into an encoder stack, so use one half of it, or we can split this into the decoder stack and use that other half. And using only half of it, like what BERT does, we take our input and we stop at that intermediate embedding space. And what that gives you is the ability to start another type of project, or what's called transfer learning. You can start with this pre-trained model that was trained just on natural English, and you can use that as your starting step for your own type of solution. And so when these projects were released, they really revolutionized and made the state of the art a brand new area for natural language processing. And we can see that in the last couple of years since these projects came out, there's been a ton of work in this area to take what BERT and GPT-2 did and really specialize it towards various types of use cases. So for example, Facebook worked on the project Roberta, which took BERT and optimized the pre-training approach for how they wanted to use it. We see a project like SentenceBERT or SBERT, which we'll be using in our project, and we'll talk in more details later, which took the word level BERT embedding and created the sentence level embedding so that we could do sentence comparison easier. Then you see things like GPT-3 and Big Bird, which are follow-ons from the same projects as GPT-2 and BERT, that take the original models and in GPT-3's case, just explodes it to an enormous size, where it went from a max of 1.5 billion trainable parameters to 175 billion. And in Big Bird's case, it tweaked the architecture so that we could use longer input sequences without hurting the performance. And just to kind of illustrate how new and how expanding this field is, SBERT or SentenceBERT, the project that we've been working on for the last year or so, within the last week, last Saturday at the time of this recording, just released a new paper on how they've improved their process to achieve better scores. So this is a brand new area. It's an exciting area, and there's a lot of cool approaches that we can use with these newly released pre-trained models. And so to kind of illustrate how this works, there's 2 steps to a typical type of use case here. The first step, which has been taken care of by BERT or GPT-2 or any of the other similar types of models, is the semi-supervised learning, where they do days, potentially weeks of training on Wikipedia, on all available books online, and they create this very rich contextual understanding of natural language. And then the second step, which is where Unisys and other companies are able to come in, is they can use that model that was already trained for them and take that as an input for a lot simpler tasks, like, for example, a classifier. Is this email a spam email or not a spam email? We don't have to worry about how to embed and contextualize the text in the email because we can use BERT for that. And so this opens up a wide variety of opportunities with really smaller investment on companies' part, where we can do tasks like language generation to maybe generate a new article when a sports game ends. You can do that automatically based off of the stats in the game. You can do language translation from, say, English to French. You can summarize documents. You can do question answering, kind of getting into the realm of chatbots. Sentiment analysis, where you're looking at, is this a positive statement? Are people on the web page, are they responding positively, giving good reviews? Are they bad reviews? And then finally, the use case that we focused on, which is the sentence comparison. So taking one sentence and another sentence and saying, are these similar? Are they not similar? And how similar are these sentences? So to do that, like we said, we used a project that came out last year called SBERT, which creates the sentence level embedding. So given a sentence like show TPM keyword, it will create a single vector in a high dimensional space that we can use to search our document space. And as an example on the right, we see how kind of cosine similarity works, where if you embed concepts like apple, banana, and a car into a 2-dimensional space, the apple and banana will be very close to each other and give a high similarity score, whereas car will be further from them and give a low similarity score. So what we're able to do here is take our query, embed it into this space, and find our most similar potential outputs that we've obtained from our documentation. And so an example of kind of what this might look like is if someone gives a query, show active transactions, where they're trying to figure out the correct syntax on our proprietary system, what is my key in to show transactions? We can match it against a set of descriptions of our potential key-ins. And then you can see at the bottom, it matches with all of the key-ins having to do with showing active transactions. And in a more general sense, you take the input query, you get a semantic embedding, search against a whole list of target sentences that you've also embedded into this space. And then when you find the sentences you want, you can suggest a correlated action with that sentence to the user. So in order to do this, really what we had to do is take our input, our document corpus, our system of user documentation, our PDFs, Word documents, and we needed to parse them into sets of trigger phrases that we could use. And as well, we discovered that since we have such a proprietary set of jargon with our OS 2200, our model also highly benefited by doing some additional training so that we could give the model our context. So in order to do that, we kind of find the most interesting, the most relevant parts of the document, and do that automatically so that at the end of this, at the end of our trigger phrases and our model training, we have both a trained database of our potential outputs, and we have a trained neural network or transformer network, which can be used against all of the queries to transform them into our semantic space. So in order to achieve both of these goals and generate both of those outputs, we had to kind of dig into our documentation space and figure out how do we extract for training our most important domain-specific terms. So the things that are unique and maybe have a different meaning within an OS 2200 context. And we found that we were able to use a lot of the existing structures within documents. So that includes glossaries, both if we have a document that's entirely a glossary, or some of our documents have glossary terms at the end. Our table of contents, which highlight really the most important parts and the high-level terms within a document. Our index, which, similar to the glossary, really references what the document writers thought was the most important part. And then there's a whole variety of tables scattered throughout the documents that often follow a format of having a term followed by the purpose or the description of that term. And so we're able to use that to really identify our list of what's the important jargon and select out the sentences that contain that jargon in context and use that to fine tune our model and get a richer embedding. Similarly, when we're trying to select out the sentences that we use for our potential targets or triggers, we were able to take advantage of a lot of the structure contained within our documents, although we do it in a slightly different way, where instead of trying to figure out which of our terms and which of our sentences in the document contain the jargon, we're trying to figure out which sentences are the best descriptors and the best representers of the things that people would search for. So in addition to kind of the parts of the document we already talked about, we also noticed that a lot of the times things like cross-references between the documents are important, or highlights, which are when you change from maybe a bold to a not bold, or a part of a sentence is italicized. That often denotes really the target of what people are trying to search for. And we also really discovered this kind of newer idea as we were doing this work of implicit tables, where we have throughout our documents these explicit tables where it follows, a traditional table format. You've got rows, columns, and you've got the clear lines between them. But you also have these implicit types of tables, which the glossary figure 1 here is a kind of a good example of, where it doesn't look like a table, but it's really easy to see if you think about it, that it is a table in the same format as that figure 3 table, where you have the term as one column and you have the purpose or description as another column, even though it doesn't really fit into that form in the document. And so with all of this together, we were able to put together a prototype based on a select portion of some of our documentation of what this could look like for our system, where a user enters a query like set TPM keyword, and using the trigger phrases that we've automatically mined out from our documentation, the top 2 results here are the 2 operator key-ins that control our TPM keyword, whether it's turning it on or off or configuring it. And so with this, we're able to not only say, okay, here's the key-in, but when we dig down into the details, we're able to point the user to, here are the documents that were most relevant, and here's the context of where we found these outputs. So our takeaways from this whole project, and really the big thing I want to convey here today, is that the new techniques that have come out in the last few years for natural language processing really do give amazing outcomes. When we started working on this, we were amazed that our first naive implementation worked out of the box. We started this idea as part of a hackfest, which our company likes to do on a regular basis, just to give the opportunity for innovation in projects like this, that we were able to get a semi-working prototype within just one day because the technology works that well out of the box. But along with that, even though the technology works really well, there's still a large challenge of getting the correct information so that we can properly utilize the technology and utilize the models. And this isn't just a natural language process or problem. This is something that we see in our work across all of our AI and machine learning solutions, where really the most important piece and the most difficult, challenging piece of all of our projects is not necessarily the technology, because the technology works and it works really well, but you need to have the right data for that technology to actually work and give you the outputs you want, and hopefully do it without major bias, which has been a problem for machine learning. And so I hope you come away from this talk with maybe some new ideas of potential use cases for your company, of how you can utilize this new technology, because it really is exciting. There really is a lot of innovation and new work in this area. And I think we at Unisys have been very pleased with our results and what we've been able to do with this technology. So I want to just again thank Jade for the time and opportunity for us to do this, and looking forward to our chat portion of this to hopefully answer some more questions and dig into other details.
I was just about to say, Mark, you're not off the hook yet. So awesome.
I figured.
Good. Well, I do have a few questions. So first question, I think a lot of folks would want to know this if this were live. You've applied this to document search, right? What are other applications with using this technology? Like, what's the next pivot that this could be implemented towards within Unisys? What's the neighbor to this, I guess, for lack of better words?
Sure. So the proof of concept that we wrapped up for this, like you said, was documentation search. And since we've kind of presented that within the company, we've seen other products in other areas come forward and say, oh, actually, we think this would be useful for us too. So one example that we had conversations just recently with is we have a content management system that they looked at this and said, oh, we have a lot of client information that we come in and store, and a lot of that is unstructured text data. Can we use this technology for our clients to be able to access and search their own data that isn't structured and isn't necessarily easy to find if you don't have the proper tagging? So that was one cool idea we hadn't considered when we worked on it, but has since kind of come to light as a possibility.
Yeah, kind of related to that. I'm curious if you could put it in plain terms, like what's the business case for implementing machine learning across Unisys in the same way you've done for the document search tool? Like, what are the tangible ways that customers will benefit, that the teams will benefit? Like, what are the easy wins here based on what you've seen with this project?
Sure. So I think one of the easy wins is it gives people easier access to data. And we've seen this not only in natural language and this proof of concept, but in some other AI and machine learning projects where we have clients that are interested in their cloud infrastructure and trying to figure out, are we utilizing our machines properly? And we've been able to see that applying some other machine learning techniques, we're able to make the recommendation that your machine is underutilized and you don't need all of your machines, or conversely, you're undersizing machine and it's impacting your productivity.
That makes sense. Whoa. Oh, did we lose Mark? Uh-oh. This has never happened before, but technology, right? Come on, folks. This has to be a
Indeed.
fluke. Kelsey, I may have to put you in the hot seat till Mark comes back in.
I'll follow on to what Mark was saying about some
Okay.
of the business use for this.
Okay.
Unisys is certainly not a startup company. We've been around for a very long time. We have some very senior staff, many of whom are retiring. And they instinctively know where to find information in the documentation, in the existing documentation. But our new folks who are coming in to the organization don't have that, 20, 30, 40 years of history. So a mechanism like this where they can ask questions using their own terminology, which then we can have the natural language processing map onto the terminology of the documentation to find the match for the intent of what they're trying to find. It's really valuable for us.
Okay, awesome. Awesome. Well, if someone wanted to sort of take on a project very similar to what you all did with documentation, what are some first immediate steps they should take? Like I'm within my own organization, I run my own team. Like, what are some of the things I need to be thinking about? What do I need to put in place to get this like jump started within my organization?
On the web, there's certainly a lot of resources for how to use BERT and SBERT technology. Literally, it's a couple of dozen lines of Python to make it work.
Awesome.
You don't have to do a lot
It's that
of
simple
programming. Yeah, exactly.
Okay.
The challenge, of course, is then to get the data to do the training of the model. That tends to be the long pole, the much harder problem to do. But just to get the model up and working and show a demonstration project, you can do very quickly.
Okay. Awesome.
And there's lots of models available on the web that you can pretty much just cut and paste.
Okay. Well, this was super, super helpful. I'm bummed that Mark can't get the recognition as we close up for the day. Are there any other things you'd want to leave with our technology community before we close out, Kelsey?
Keep exploring, especially in this area that is changing so very quickly, and see how your organization might be able to leverage it for best effect.
Okay. Awesome. Well, thank you so much. Thank you to Unisys. Thank you to you, Kelsey. Thank you to Mark. We're excited to share this with the community. And for folks who have tuned in with us, thanks for hanging out by the fire as we talked about all things stories and machine learning. Have a good rest of your, day, morning, whatever time it is as you watch this.
And thanks to
Adios.
you. Thanks to you and MnTech for hosting this series.
Thank you. Have a good one, Kelsey.
Bye.